Hello and welcome to the fourth video, Measurement Parameters and Instrument Configuration. Now that we have looked at the purpose of measurements, the measurement equipment, and the measurement points in the previous videos, let us now discuss what exactly you wish to measure. Remember to familiarize yourself with the instrument, read the instructions, and do some trial and error tests before going out into the field and carrying out work for clients. Let us start off with the simplest one, voltage measurements. If you are performing quality of supply measurements, it is very likely that you will only be concerned with voltage measurements. Typically, for quality of supply, you would be concerned with the voltage regulation. And here's a typical graph of voltage regulation. This is your daily voltage profile given as a percentage of nominal voltage, which is 100 volts. Then the next one is your voltage unbalance. And here we have voltage unbalance, which we explained in the first slide, given a formula of how to calculate it. And it's really a quality of supply parameter that you would be measuring. And then frequency, which you would only have that as an event capture with certain instruments if it goes out of frequency limits of plus or minus 2.5%. And then your next one is your voltage harmonics. And here's a profile of your total harmonic distortion. You can get the individual harmonics as well if you want third harmonic or fifth harmonic or seventh harmonic or 15th harmonic, whichever one you want. And then next is your voltage spikes or surges. And there we explained the voltage spikes and surges as well in the first video. And we talked about these events. Okay. And these, obviously, we mentioned requires a very specialized equipment that is able to measure high frequency events. And then the other one is flicker, which is also specialized equipment. And in order to measure flicker, it's usually carried out by a specialist that has such equipment. So most standard power analyzers don't have a flicker measurement function. So the correct phasing is very important when you are measuring. And by correct phasing, we mean ensure that your A phase is connected there, your B phase is there, and your C phase is connected there, because it's going to give you a proper vector diagram. When measuring any of the above parameters, all you need is correct phasing of your voltage connections. Once that is done, setting your measurement limits is absolutely essential. If you are measuring quality of supply specifically, there are instruments designed specifically to measure to the known quality of supply standards. In South Africa, we have the NRS 048 series of specifications with specific measurement requirements which define the sampling rates and averaging of data, including the reporting for specific periods. There are a number of instruments that are made to measure in accordance with those exact specifications and output reports in the NRS 048 required formats. So we have NRS 048, quality of supply, and then the IEEE and IEC, they have a number of standards that deal with different power quality aspects, and there should be local guidelines in most countries which are derived from IEEE and IEC, like the NRS in South Africa. So the NRS has been derived from international standards, and it's not just something that came out in South Africa. And whichever country you are in, there should be a local standard, or otherwise they adopt the IEEE or IEC standards. You may also just want to measure voltage for specific problems, such as continuous undervoltage or overvoltage. In my recent experience at home, I had appliances not performing properly, fans running slow, microwave oven not heating. And when I tested the voltage, I found that my house was getting 180 or 190 volts on a 230 volt system. You may have customers where they experience similar issues at their places of business. So you have a profile and you have undervoltage that could result, okay, not as severe as the way I've drawn it here, but you may deviate by 15 or 20%, as much as that. And that's going to affect all your equipment, it's going to affect your appliances, and it might even damage certain equipment. Now, a very common one is voltage spikes. And these result in the failure of sensitive equipment or lighting. In this case, you would need an instrument capable of capturing a few hundred samples per cycle. That is a sampling rate in the microseconds. Instrument presets usually have the correct range for data capture speeds for whichever parameters you want to measure. So if you are measuring spikes and you select that option, the instrument will be able to capture very high frequency events. You may need to specify an upper voltage limit to trigger the recording. For instance, 2 times nominal system voltage, which is 2 times 230 volts, which is 460 volts. It is also helpful that if you are testing for failure of specific equipment, that you try to obtain the specifications for that equipment to see what its voltage tolerances are. Then you can set up the recording to measure for any anomalies outside of those tolerances. So in this example, if we have 230 volts here, and we have 460 volts here, and we want our instrument to trigger at that value. So as soon as the voltage spikes above 460, it will give you a recorded event. And your event should be recorded in the form of a date and time and the duration of the event, and it will give you a magnitude. Now in a case like this, you might want to go 1.5 times the voltage and not 2 times. Because 1.5 is already enough to damage a lot of equipment and cause problems. So you might even go 1.5 times. Now the example is if there is a large-scale printing machine which requires a voltage that's within plus or minus 5% of 230 volts. Then you need to set up your instrument to trigger when voltages go outside of that limit. Usually for standard regulation, a utility is only required to provide a quality of supply of within plus and minus 10% of nominal voltage. Now, if you have a utility supply that's not very reliable, and you know that your voltage is going to go out of those limits very often, then you want to measure for that and take preventative measures. So for sensitive equipment, one would usually connect the equipment through an automatic voltage regulator or through online UPS, not a line interactive. So if we look at this profile here, we have 100% here, which would be, in our case, 230 volts. And then if we go 5% above here, which will give us 242 volts, okay? And if we go here, minus 218 volts. So if we have equipment that's sensitive and that's going to go out of those limits, then we want those events to be triggered. Okay. For example, examples of limits for 230 volt systems include plus minus 5%, upper trigger, as we've mentioned here, 242, lower trigger at 218. And then you might want to measure voltage harmonics. And you might say that you want your harmonic trigger to be at total harmonic distortion above 8%. So what happens in these cases is, let's assume we have a large load that starts up every day at around this time. Then we can actually capture those events. Okay, and we will speak about this in a little bit more detail just now. So setting of limits and times will require you to do your homework beforehand, knowing the capabilities of your equipment. The time of the recorded trigger event will also give you a good indication of what happened during the time of the trigger occurred. You could ask your client what specific operation took place when the anomaly is triggered, and this helps in pointing to the possible causes. So as we've shown these anomalies here, if we are getting this sort of voltage dip every day at around the same time, then it's likely that there is a very high powered load starting up at that time, and it's causing the voltage to dip, and it's causing a trigger. As we mentioned previously, it will give you a trigger date, time, duration, and magnitude. And then it's easy to go to the client and say, okay, what actually happens in your operation during 10 a.m. every morning? And that gives you an idea of what is happening and what steps you need to take to prevent it. So now let's look at current measurements. Here you would most commonly be looking for the amps. Okay, and here we have your graph of your amps during a 7-day period. And then you'll be looking for your watts. And there's your watts associated with your amps for your 3 phases. And then you'll be looking at your VARs, which is your reactive power. And you'll be looking at your VAs, which is your apparent power. And then you'll be looking at your power factor during the entire measurement period. Now let's assume that you want to add new loads to an existing distribution point, and you want to determine if there is spare capacity on the feeder cable. You would install your current clamps, as previously discussed, onto the correct feeder cables, phases, conductors with the appropriate CT ratios. So in this case here, you have your 3 phases connected to your three phases of your outgoing feeder cable at the bottom of the circuit breaker, and you would ensure that you select the correct CT ratio for the measurement. Now for load measurements, you would likely select a measurement interval of 5 or 10 minutes. This means that the instrument continuously measures in milli or microseconds for 5 minutes and then averages the data into a single 5-minute value. Now that's only going to give you an averaged value over the 5-minute period. Then you would probably also want to select the max values during every 5-minute intervals to see if there are any long periods where the phase load is higher than the average load. That is very important because the short increase in load could be even half a second, 1 second, but averaged over 5 minutes, it looks like there hasn't been a sharp increase in the load. So it's very important that you also select maximum values. So let's talk about upstream measurements. So it's very essential to note that when doing this type of measurements, you always need to also ensure that there is spare capacity upstream of the point you are measuring. If you are measuring a 125 amp circuit breaker and feeder, and the highest average reading for a specific period is 60 amps, and the max value during the period is 65 amps, and you wish to add a calculated load of 15 amps, then this feeder can likely take the additional load after you have considered derating and fault drop on the feeder. So assuming we have here a 125 amp feeder, and we are measuring here, and we're getting an average of 60 amps, and we are getting a max of 65 amps. And we want to add another 15 amps to this feeder. And it looks like this feeder will be fine because we take our average to 75, our maximum to 80, and we should be fine. Okay. However, what if this feeder is supplied by a transformer that can deliver 500 amps max, and the load at the main feeder from the transformer is already at 470 amps? Then it may not be a very good idea to add load to this feeder. So let's assume here we have a 500 amp supply, and this 500 is already at 470 amps. So if you add another 15 amps, you're taking it to 485, and it's not recommended to take it to that value. That is why it is essential to measure both points. Understanding your network configuration is very important before doing any measurements. And now this also applies further upstream of this, because let's say you are within limits here, but what about further upstream of this? Are you going to be fine there? You also may want the power factor readings so that you can provide data to a power factor correction supplier to design the appropriate PFC system. They would require information such as the average power factor profiles, the average load, as well as the current harmonics to size the system and ensure that the design of the capacitance does not result in harmonic resonance. That is where harmonics get amplified by the power factor correction. To get the power data accurately, You must ensure that your connections are correct and your displayed vector diagrams of volts and amps is correct. Otherwise, the power and the power factor data will be completely wrong. We will discuss this very critical aspect in the installations section. So we previously spoke about your vector diagrams, and you have your 3 voltages and you have your 3 currents displayed from there, and you've got to ensure that this is correct. Otherwise, your power factor data will be incorrect and all your power data will be incorrect. Measurements may also be required very sensitive investigation work, such as for determining protection systems on MV settings. So in order to do that, you would have to measure. You would have to know the dynamics of operation of the system being supplied by the feeder and protected. Example, the startup currents for direct online loads, the duration of startup currents, the time setting for under voltage protection due to startup. When does an auto voltage regulator have to kick in during startup of heavy loads, and when to have it kick out of the system to prevent overvoltage trips? There are many site-specific conditions that can be investigated through high-speed measurements. So let's have a recap. We discussed the voltage measurement settings and the correct phasing. Then we've covered high-frequency events. Then we've talked about current measurement settings and correct phasing. And we talked about specialized measurements. Now, in our next videos, we will look at on-site connection and safety, instrument configuration on-site, and reporting. Thank you, and I'll see you in the next video.